Your robotic mower just beamed another 1,000 data packets to the manufacturer's servers before sunrise while sitting idle. I know because I watched mine do exactly that for 2 weeks straight before I pulled the plug, literally. Once you start packet sniffing your yard equipment, you can't unsee how chatty these things are with corporate headquarters. I'm Chelsea Miller, and I rebuild smart home systems from the ground up when I discover they're surveillance devices disguised as convenience.
You're listening to Smart Home Setup Podcast. Quick transparency note before we dive in. The research, the testing, the script you're hearing, all of that's human work, verified and written by actual people who use this stuff. The voice delivering it is AI generated, which lets us get these episodes out consistently without compromising the depth of content. Just wanted you to know what you're listening to. If you've been subscribing for a while, seriously, thank you. Means more than you'd think. And if you just found us, hey, welcome. Glad you're here. We drop new episodes every Monday, Wednesday, and Friday covering privacy-first smart home automation without the usual corporate talking points. Today, we're getting into robotic yard equipment, which turns out to be some of the chattiest, most cloud-dependent hardware you can buy. Let's fix that. Welcome to the world of local-only yard automation, where your grass gets cut without Amazon, Google, or equipment manufacturers tracking every blade. This guide walks you through connecting robotic yard equipment to your smart home hub the right way. No cloud dependency, no data leakage, no manufacturer permission required. I'll show you the protocols that actually work, the automations worth building, and the privacy traps you need to sidestep. Fair warning up front, this is intermediate level work. You'll need basic networking knowledge and comfort editing configuration files. Plan on 3 to 5 hours for initial setup, then another 2 or 3 hours refining automations based on how your specific yard behaves. I'm covering local-only integration methods for robotic yard mowers, smart irrigation controllers, and autonomous landscaping devices, plus the honest truth about which equipment can actually function when you cut the internet cord. Let's start with what you'll need. First, a privacy-respecting smart home hub running Home Assistant, Hubitat, or similar local-first platform. Cloud-only hubs like SmartThings won't cut it here. You need real local control, not cloud control with a local label slapped on. You'll need robotic yard equipment with a documented API or protocol support. I tested with 3 devices. Check the link below to see the current price for the Husqvarna Automower 450X EPOS, the Works Landrid M20V, and the Ratio 3 Smart Sprinkler Controller. You'll also need protocol hardware matching your equipment, Zigbee, Z-Wave, or Thread coordinator if using those protocols, or Ethernet and Wi-Fi capability for IP-based devices. Network isolation tools are critical. A VLAN-capable router or firewall rules to block internet access for yard devices. Set up an MQTT broker, Mosquito works well, for local message passing between devices. You'll need basic Linux command line familiarity for editing config files and checking logs. Grab some outdoor-rated smart plugs, preferably Zigbee or Z-Wave, for power cycling equipment remotely. A weather station or integration providing local precipitation data without cloud dependency. And patience for firmware extraction, because some devices require custom firmware to eliminate their constant phoning home behavior. Now, let's talk about auditing your equipment's cloud dependencies. Before you can properly integrate robotic yard equipment, you need to know what you're up against. I spent 2 weeks packet sniffing my Husqvarna Automower before integration and discovered it attempts to reach Husqvarna servers every 47 seconds, even when the mobile app isn't open. Not occasionally, not when needed, every 47 seconds, like clockwork. Set up network monitoring using Wireshark or your router's logging function. Block all outbound traffic from your yard equipment's MAC address and carefully observe what breaks. Take detailed notes as you test. Does the device boot without internet access? Some equipment flat out refuses to complete initial setup without cloud authentication. What functions fail when offline? GPS coordinates, weather data, and mobile app control are common casualties. Does it implement local protocols? Check for MQTT support, REST APIs accessible on local IP addresses, or documented Zigbee and Z-Wave capability. How does it handle DNS failures? Quality devices continue operating when DNS fails. Poorly designed ones crash or enter safe mode and sulk. The Husqvarna required custom firmware to fully eliminate cloud dependency. Warranty voiding, but absolutely worth it in my case. The Works Landroid has an undocumented local API that works perfectly when internet access is blocked. Works just doesn't advertise this capability anywhere. The Rockio grudgingly accepts local MQTT commands, but constantly complains about lost connectivity in its logs, like a toddler denied dessert. Document every DNS query, every failed connection attempt, every port scan your equipment attempts. This data determines whether your equipment can truly integrate locally or whether you're building on a foundation of perpetual cloud nagging and eventual failure. For a comprehensive breakdown of yard automation options beyond just mowers and irrigation, check the link below for our guide to autonomous yard landscaping technology. Moving on to network-level containment. Your robotic mower doesn't need to talk to Amazon, Google, or equipment manufacturers to cut grass. It needs power, location data, and collision avoidance, all available locally on your network. Containment prevents privacy leakage and forces you to solve integration problems the right way instead of taking lazy cloud shortcuts. Create a dedicated VLAN for yard equipment on your router. Most modern routers support this natively. For older hardware, consider adding a managed switch. Configure firewall rules with precision. Allow LAN access for hub communication. Your yard VLAN needs to reach your Home Assistant IP on port 1883 for MQTT and port 8123 for HTTP API. Allow your local MQTT broker IP on port 1883. Allow your local DNS server on port 53, but only for local resolution, not forwarding to external DNS. Block all internet-bound traffic from the yard VLAN to WAN on all ports. Optionally, allow NTP for time synchronization. You can use a local NTP server for this if you're thorough. Test connectivity by attempting to access manufacturer cloud services from a device on the yard VLAN. Everything should fail. Your hub should still see yard devices perfectly fine because they're on the same local network infrastructure, just isolated from WAN access. I use Unify networking gear, which makes VLAN management straightforward through a graphical interface. If you're using pfSense or OpenSense, the principle is identical, but configuration happens via different interfaces. The key outcome you're looking for, your robotic mower can see your Home Assistant server at whatever local IP you've assigned it, but cannot reach Husqvarnagroup.com, WorksLandroid.com, or any telemetry endpoint the manufacturer operates. Latency expectations here are important. LAN communication adds essentially zero latency, typically under 2 milliseconds for local MQTT messages versus 150 to 800 milliseconds for cloud round trips. Reliability skyrockets because you've eliminated internet outages, DNS failures, and manufacturer server downtime from your possible failure modes. Learn more about testing actual response times in the link below for our device latency testing guide. Next up, choosing your integration protocol. Most robotic yard equipment uses one of 4 connection methods. Your choice determines flexibility, reliability, and how much manufacturer nonsense you'll tolerate. The most common method is Wi-Fi with local API. Equipment like the Works Landroid and many smart irrigation controllers expose REST APIs or WebSocket interfaces on local IP addresses. Once network contained, these become reliable integration points. Here's a Home Assistant configuration example. In your configuration.yaml file, you'd define REST commands. For mower start, you'd specify the URL as your mower's local IP address at the API version 1 start endpoint, method post, with an authorization header containing your local bearer token. For mower return, same structure, but hitting the return to base endpoint. Latency for local HTTP commands typically runs 15 to 40 milliseconds. Reliability is excellent if your Wi-Fi coverage extends to the yard. Poor if it doesn't. Use outdoor-rated access points or mesh nodes to eliminate dead zones in your coverage. Fallback behavior is generally good. Most equipment returns to its charging station when connection fails, which is exactly what you want. Another option is Zigbee or Z-Wave smart plugs for power control. When your equipment lacks local protocol support entirely, crude power control still enables basic automations. I use Azu's Zen 15 power switch, which is Z-Wave Plus, on my older irrigation controller. Check the link below to see the current price. The automation logic is simple. If the time equals 6 a.m. and weather precipitation is less than 2 millimeters, then turn on the irrigation power switch, wait 20 minutes, turn off the irrigation power switch. This approach works for any yard device drawing under 15 amps. Latency for Z-Wave commands runs 80 to 200 milliseconds, slightly faster for Zigbee. Reliability for mesh protocols depends heavily on node density. I have 6 outdoor Zigbee repeaters and rarely see command failures. Fallback behavior is straightforward. When the hub crashes, power remains in last state, either on or off depending on when failure occurred. You want normally off for safety. For detailed protocol comparisons, check the link below for our Zigbee versus Z-Wave smart plugs analysis. MQTT is the gold standard for sophisticated control. Some equipment, Ratio, certain robotic mower modifications, supports MQTT natively or via custom firmware. The automation logic becomes elegant. You subscribe to Home Assistant Yard Soil Moisture and Home Assistant Weather Rain Today topics. If soil moisture drops below 30% and rain today equals 0, then publish to mower pause with payload true, publish to irrigation zone 1 start with payload 900 seconds for 15 minutes, wait 15 minutes, publish to irrigation zone 1 stop, then publish to mower resume with payload true. Latency for MQTT is under 10 milliseconds for local broker message passing. Reliability is excellent. MQTT's lightweight publish-subscribe model is extremely reliable on stable networks. Fallback behavior depends on implementation. Devices should cache last known state and continue operating. Verify this by killing your broker during testing and watching what happens. The emerging option is Matter and Thread for outdoor equipment. As of 2026, yard equipment manufacturers are finally adding Matter support, though it's mostly limited to irrigation controllers and smart hose timers. The Eve Aqua Smart Water Controller uses Thread, which requires a Thread border router like HomePod Mini or certain Google Nest devices, and integrates seamlessly with Matter-compatible hubs. Check the link below to see the current price. Thread offers 15 to 30 millisecond typical command response. Reliability is solid. Thread's self-healing mesh is extremely reliable on stable networks. But you need adequate border router coverage in outdoor spaces. Expect to add dedicated Thread repeaters for larger yards. Fallback behavior follows the Matter spec. Devices must maintain last automation state when controller disconnects. For comprehensive Matter setup requirements, check the link below for our Matter 1.4 Hub Requirements Guide. The protocol you choose affects how you connect robotic yard equipment to your smart home hub more than any other single decision. I use MQTT wherever possible, fall back to local APIs when MQTT isn't available, and avoid cloud-only equipment entirely. Now we get to the fun part. Extracting or generating API credentials. This is where manufacturer hostility becomes painfully obvious. Companies want you trapped in their apps, funneling data to their servers. You want control files and API tokens for local access. These goals conflict directly. For equipment with documented APIs, the process is relatively straightforward. Ratio publishes API documentation, though they'd clearly prefer you didn't use it for local access. Generate an API key through their web interface, then immediately block internet access. Test local API access before cutting internet with a curl command to your device's local IP on port 8080, hitting the API version 1 zones endpoint with your authorization bearer token in the header. If that works, block WAN access and retest. It should still function because you're hitting the local device, not their cloud servers. For equipment with undocumented APIs, you'll need to do detective work. The Works Landroid's local interface exists but isn't publicized anywhere in their documentation. I discovered it by running Nmap against the mower's IP address, finding open port 80, and reverse engineering the mobile app's traffic patterns. Port scan your equipment across all 65,000 plus ports. Found open ports? Try common HTTP endpoints like status.json, API version 1 info, or similar REST paths. Most equipment responds to status, info, config, or similar REST endpoints. Authentication might be basic auth, bearer tokens, or sometimes hilariously non-existent. Packet capture the mobile app during normal operation to identify correct headers and payloads. For equipment requiring custom firmware, things get serious. My Husqvarna mower needed open mower firmware to achieve true local control. This voids warranties and requires comfort with bootloader access and serial console connections. I'm not providing step-by-step firmware flashing instructions here, that's its own article, but recognize that some equipment simply cannot be locally controlled without modification. You need to decide if that trade-off works for you. Security note worth mentioning, extracting API credentials sometimes reveals hilariously bad security practices. One irrigation controller I tested stored my Wi-Fi password in plain text in a file called network.txt, accessible via unauthenticated HTTP. Just sitting there. Anyone on the network could grab it. I reported it to the manufacturer. They ignored me completely. Consider all yard equipment potentially compromised and isolate accordingly. Let's build some core automations with explicit logic. Now the actual integration work begins. I'll show you functional automation patterns I use daily with transparent if-then logic you can understand and modify. First, smart mowing schedule with weather integration. In Home Assistant YAML, you'd create an automation with alias adaptive mowing schedule. The trigger is time-based at 6 a.m. Conditions check that precipitation in the last 24 hours is below 5 millimeters of rain, soil moisture in the front yard is below 70% saturation, and grass height estimate is above 45 millimeters. Grass height is derived from a growth model based on temperature plus rainfall plus last mow date. Actions call the mower start rest command and send a persistent notification with timestamp. Why this matters? Blindly running schedules wastes energy and tears up wet grass. This automation checks precipitation, soil moisture via Zigbee soil sensors, link below for our guide on covert smart home sensors, and estimated grass height before starting. Expected latency is under 500 milliseconds from trigger to mower receiving the start command. Fallback is safe. If conditions aren't met, mower stays in dock. Second automation, coordinated irrigation and mowing. Robotic mowers and sprinklers conflict badly. I learned this the hard way when my mower tried cutting a freshly watered zone, left deep ruts in the mud, and spent an hour extracting itself. The automation triggers at 5:30 a.m. Condition checks that soil moisture in Zone 1 is below 35%. Actions: pause the mower if running, delay 2 minutes to let the mower reach its dock, start irrigation Zone 1, delay 15 minutes for watering, turn off irrigation Zone 1, delay 2 hours for ground to absorb water, then resume mowing if it was previously active. This eliminates equipment conflict completely. Mower pauses and docks before watering starts, remains docked during watering plus a soak period, then resumes. Latency for mower pause and dock takes 60 to 120 seconds, depending on current location. Plan your delays accordingly. Fallback is conservative. If mower fails to pause due to API timeout, irrigation won't start. I'd rather skip one watering cycle than damage my yard. For more on irrigation logic, check the link below for our guide to smart irrigation zones and scheduling. Third automation, energy-aware charging management. Robotic equipment draws 50 to 150 watts while charging, meaningful if you're on time-of-use electricity rates or running solar power. First automation triggers when electricity rate period changes to off-peak. Condition checks that mower battery percent is below 80. Action turns on the mower dock power via a Zigbee smart plug. Second automation triggers when rate period changes to peak and simply turns off mower dock power. I control dock power via a Zooz ZEN15, which also monitors power consumption. Link below for our guide on best smart plugs with energy monitoring. Latency for charging control response is instant, Z-Wave command under 200 milliseconds. Reliability has been flawless for 18 months of operation. Fallback is appropriate. Smart plug defaults to on if hub fails, ensuring mower can always charge. Losing peak versus off-peak optimization is acceptable. A dead mower battery isn't. Learn more about similar optimizations in the link below for smart home energy management. These automations represent months of refinement and real-world testing. Start simple, add complexity only when you understand failure modes for your specific setup. Now, let's implement monitoring and failure alerts. Local control eliminates manufacturer servers as failure points, but introduces new ones. Your hub, your network, your power supply, any can fail. Smart monitoring catches problems before your lawn resembles a jungle. Device availability monitoring uses a binary sensor in Home Assistant with platform ping, targeting your mower's IP address. Count 3 pings, scan interval 60 seconds. The automation triggers when the mower Network Alive sensor goes to off state for 5 minutes. Action sends a mobile notification stating mower offline since the timestamp. Why ping matters? A mower that stops responding is either crashed, stolen, or stuck somewhere. 5 minutes of non-response warrants investigation. Latency for detection is 5 to 6 minutes due to the 60-second scan interval plus 5-minute confirmation period. Fallback consideration: if Home Assistant itself crashes, you lose monitoring. Consider a separate watchdog system for critical infrastructure. Energy consumption anomaly detection leverages smart plugs with energy monitoring. The automation triggers when mower dock power rises above 200 watts for 10 minutes. Normal charging is 50 to 80 watts, so this indicates a problem. Action turns off mower dock power and sends a persistent notification about abnormal power draw and disabled charging for safety. I added this after my mower's charging circuit partially failed, drawing 250 watts and heating the dock dangerously. This automation cut power automatically before damage occurred. Expected behavior is triggering within 10 minutes of anomaly onset. Reliability is excellent. Energy monitoring rarely produces false positives. Fallback is appropriate. Cutting power to a malfunctioning charger is always safer than letting it continue. Weather-based operational boundaries add another safety layer. The automation triggers when wind speed exceeds 40 kilometers per hour. Actions: send mower return to base command, turn off irrigation master valve, and notify via mobile app that yard equipment was secured due to wind speeds. High winds blow debris onto sensors, reduce GPS accuracy, and increase collision risk for robotic equipment. This automation docks everything when conditions deteriorate. Data source: I use a local EcoWit weather station feeding Home Assistant via local API with no cloud dependency. Latency is excellent. Wind speed updates every 16 seconds, total reaction time under 30 seconds. Fallback consideration: if weather station fails, automations continue with stale data. Consider adding staleness detection for critical weather inputs. Monitoring transforms connecting robotic yard equipment to your smart home hub from a weekend project into a reliable, maintainable system. Without monitoring, you're flying blind. Next critical step: test failure modes and document fallbacks. Your automations work perfectly until they don't. I force fail every component in my yard automation stack annually, documenting what breaks and how equipment responds. You should too. For network failure scenarios, test by unplugging your network switch or disabling the yard equipment VLAN. Mower behavior varies by model. Most robotic mowers continue their current task when network disconnects, then return to dock when task completes or battery depletes. The Husqvarna continued mowing through the entire network outage. The Works immediately docked, which is overly conservative but safe. Irrigation controller behavior also varies. My Rockio continued running active zones to completion, then stopped scheduling new zones. Perfect fallback behavior. Cheaper controllers sometimes crash entirely. Test yours specifically. Smart plug behavior is predictable. Z-Wave and Zigbee devices maintain last state when hub disconnects. This is critical for power control because you don't want charging to randomly stop mid-session. Document your findings in a fallback behavior matrix, listing every device and its offline response. This informs automation design. If your mower crashes when disconnected, you need different network architecture than if it continues operating autonomously. For hub failure scenarios, shut down Home Assistant completely and observe. Equipment should continue autonomous operation based on last configuration. Time-based schedules fail because no one's sending commands. Smart plugs remain in last state, which is good for power but bad for time-sensitive switching. MQTT devices might cache messages or might discard them depending on QoS settings. This varies by implementation. My yard survives 24 to 48 hours of hub downtime before manual intervention becomes necessary. Equipment charges normally because the smart plug defaulted to on, but adaptive scheduling stops completely. I can manually trigger tasks using physical device buttons if needed. Check the link below for our device fallback behavior checklist for comprehensive testing procedures across all device types. Power outage recovery testing is essential. Cut power to your yard equipment at the breaker, wait 10 minutes, restore power, and watch carefully. Mower behavior: should auto-resume previous schedule or return to idle state. Test whether it remembers partially completed tasks or starts fresh. Irrigation controller behavior: most reset to safe off state, which is appropriate. Some controllers helpfully resume interrupted cycles, potentially flooding your yard hours after the original schedule. Smart plug behavior: Z-Wave and Zigbee devices should reconnect to mesh within 60 to 90 seconds and accept commands. Wi-Fi devices take longer, 120 to 180 seconds typical. After my last power outage, I discovered my irrigation controller resumed a half-finished cycle 3 hours after power returned, watering already saturated soil for the remaining zone runtime. Now I verify cycle completion status before starting new runs by checking that irrigation cycle status equals idle, not interrupted or running. Testing reveals reality. Marketing materials promise graceful degradation. Actual behavior often disappoints dramatically. Test rigorously before trusting your $2,000 mower to autonomous operation. For broader context on building resilient automation systems, see the link below for our smart home compatibility checklist. Let me share some pro tips and common mistakes I've learned the hard way. Mistake number 1. Assuming local API means local control. Many so-called local APIs still require internet authentication or cloud token validation behind the scenes. Block internet access during testing to verify true local operation. I wasted 3 entire days debugging a Rakio integration before realizing it quietly falls back to cloud authentication every 72 hours, even when using what they call local mode. Pro tip: GPS drift will absolutely ruin your boundaries. Robotic mowers using GPS, especially EPS systems, experience 30 to 80 centimeters drift depending on atmospheric conditions and satellite geometry. Don't set boundary wires exactly at pavement edges. Leave a 50-centimeter buffer or you'll constantly repair sidewalk gouges. I learned this expensive lesson when my Husqvarna mapped perfect boundaries on a calm day, then drifted onto my concrete patio during a solar storm and chewed up the edges. Mistake: over-automating before understanding baselines. Run equipment manually for 2 to 3 weeks before building complex automations. Learn how long zones actually need watering in your soil, how fast your grass grows at different temperatures, how your specific mower handles obstacles in your specific yard. My initial irrigation automations overwatered by 40% because I trusted manufacturer runtime recommendations instead of measuring actual soil saturation. Pro tip: MQTT quality of service settings matter enormously for yard equipment. Use QoS 1, which means at least once delivery, for critical commands like stop or return to base. QoS 0, best effort delivery, is fine for status updates that happen frequently anyway. A lost pause mowing command during irrigation startup caused the exact mud rut disaster I described earlier. Mistake: ignoring protocol latency for time-sensitive coordination. Wi-Fi's variable latency, ranging from 15 to 200 milliseconds, makes precise timing impossible. When coordinating mower pauses and irrigation starts, add generous buffers. I use 120-second delays, even though typical command response is under 30 seconds. The one time you hit 180 millisecond latency will be exactly when your mower drives through an active sprinkler. Pro tip: physical kill switches beat automation failures every time. I installed a weatherproof Zigbee button near my back door that immediately docks the mower and cuts all irrigation power with one press. Automations fail for countless reasons. Physical overrides don't. This has saved me twice when unexpected guests needed the yard cleared instantly, and I didn't have time to troubleshoot why an automation wasn't firing. Mistake: neglecting mesh network coverage outdoors. That Zigbee coordinator works great inside your house. Outside, it struggles to reach equipment 50 meters away through walls and landscaping. I deployed 5 outdoor-rated Zigbee repeaters, basically weatherproof smart plugs powered by exterior outlets, to achieve reliable coverage across my entire yard. Map your mesh coverage before assuming commands will reach equipment. More on this in the link below for our Mesh Network Reliability Guide. Let's tackle some frequently asked questions. Can I integrate robotic yard equipment without voiding warranties? Most manufacturers void warranties if you modify firmware or block cloud connectivity, though they rarely enforce this unless you're seeking warranty service for a network-related issue. Using published APIs typically doesn't void warranties because you're accessing documented features, just not through their preferred app. Flashing custom firmware like OpenMower or ESP Home conversions definitely voids warranties. I chose local control over warranty coverage. You might not make the same choice. For what it's worth, I've had 0 hardware failures in 18 months of cloud-blocked operation, suggesting manufacturer warnings about required cloud connectivity are a liability theater rather than technical necessity.
What happens to robotic mowers when smart home hubs fail completely? Quality robotic mowers continue autonomous operation using onboard schedules and sensors when external control fails. They're designed to handle GPS outages, network failures, and controller disconnects as normal operating conditions. The Husqvarna Auto Mower maintains its last programmed schedule and continues mowing independently for weeks if my hub crashes. Check the link below to see the current price. Cheaper models might dock and refuse to operate without external commands. Test yours by intentionally disconnecting it for 48 hours and observing behavior. The worst behavior I've encountered was a budget mower that beeped incessantly when it couldn't reach its cloud server, but still completed mowing tasks. Check the link below for our smart device fallback behavior guide for systematic testing procedures across all device types. Which smart home protocols work best for outdoor yard equipment in 2026? Thread and Matter are becoming the dominant choice for new outdoor equipment due to superior range and self-healing mesh properties compared to Zigbee, but equipment selection is still quite limited. Z-Wave has excellent range, over 100 meters with clear line of sight, but few native yard devices exist. You'll mainly use Z-Wave for power control via smart plugs. Zigbee offers the most device variety currently, but requires dense repeater networks for reliable outdoor coverage. Wi-Fi provides the highest bandwidth for video-enabled equipment, like security-integrated mowers, but range and reliability vary wildly depending on access point placement. I use Thread for new purchases, Z-Wave for power control, and reluctantly accept Wi-Fi for equipment without better options. Avoid proprietary RF protocols. Various mower manufacturers use custom 900 MHz systems that you cannot integrate without manufacturer cooperation. How do I prevent robotic yard equipment from becoming privacy liabilities? Network containment is absolutely non-negotiable. Dedicated VLAN with no WAN access, blocked DNS queries to manufacturer servers, and regular packet capture audits to verify compliance. Many devices will attempt to phone home for months after you block internet access. I still see connection attempts from my Works mower 18 months into isolation. Use equipment that offers local APIs or documented protocols rather than cloud-only control. Prefer wired Ethernet connections over Wi-Fi where possible because there are fewer wireless interception opportunities. Disable all usage analytics and improvement program options in device settings. Even disconnected devices sometimes cache this data for later upload when connectivity is restored. Consider that yard equipment with cameras, some high-end mowers include obstacle recognition cameras, represents significant surveillance risk if compromised. I personally avoid camera-equipped yard devices entirely, but if you use them, verify that video processing happens on device rather than uploaded for AI enhancement. For more privacy-first smart home strategies, see the link below for our comparison of subscription-free security systems. Let me wrap this up with a summary. You now know how to connect robotic yard equipment to your smart home hub without surrendering control to manufacturer clouds. Network containment isolates devices from internet access. Local APIs enable sophisticated automations when you take time to find and use them. Explicit failure testing ensures reliability when things inevitably go wrong. The automation patterns I've shared, weather-aware scheduling, coordinated irrigation and mowing, energy-conscious charging, represent real-world refinements from 18 months of local-only operation in my own yard. Cloud-free viability score, 7 out of 10. Modern robotic yard equipment can absolutely function offline with proper integration,
But manufacturers actively resist local control through undocumented APIs, firmware that constantly complains about lost connectivity, and deliberately hobbled local features. Budget another 15 to 20 hours beyond basic setup for dealing with manufacturer hostility, building robust monitoring systems, and thoroughly testing failure scenarios. The privacy payoff is worth it, in my opinion. I haven't sent a single data packet to Husqvarna, Works, or Rachio servers since completing my migration, and my lawn care automations are more reliable than they ever were when cloud dependent. Start with one piece of equipment, prove local control works for your specific setup, then expand from there. Your yard doesn't need Silicon Valley's permission to look good.
That wraps up this episode of Smart Home Setup Podcast. Thanks for listening all the way through. This was a long one, but yard automation gets complicated fast when you're doing it right. New episodes come out every Monday, Wednesday, and Friday, so you've got a steady stream of local control content if this approach resonates with you. Real quick, if this episode was useful, I genuinely appreciate a 5-star rating and a review. Not just for ego reasons, but because that's legitimately how people find the show when they're searching for privacy-focused smart home information. And hit subscribe or follow so you get notified the moment new episodes drop. See you next time.